Welcome back, and this is the first in a series of packs looking at organic chemistry. Organic chemistry, along with physical and inorganic, build up the complete picture of chemistry itself. It's a very important topic, and you should notice that it has a yellow cover. The reason for this is it's a paper 2 topic. We're going to start with the alkanes. That's the simplest hydrocarbons in organic chemistry. But before we look at the alkanes in any detail, we're going to be looking at the basic principles of organic chemistry, including how to name organic molecules. So in this first section, the introduction to organic chemistry, we're going to be looking at naming and drawing organic molecules. And you need to be able to do this up to C10. So you should be able to name any organic compounds with 10 or less carbons. So the first thing that you have to understand is that alkanes are what we call hydrocarbons. Now these are compounds containing hydrogen and carbon only, and it's important that you've got that only bit in there. There are other organic compounds like alcohols, for example, which are not hydrocarbons because they contain the element oxygen. Organic chemistry is the study of the compounds of carbon. You could also call it the study of life itself. All living organisms are based on carbon. In fact, any living organism in the universe will be based around carbon chemistry. Carbon has the unique ability to form chains and rings which are particularly stable, and this allows us to build the backbone of biology. So, for example, DNA and RNA are both organic compounds. They both contain a chain of carbon atoms. So the electron configuration of carbon is this: 1s2, 2s2, 2p2. There are 4 bonding pairs of electrons, so these electrons are in the outer shell of carbon, and they allow us to form 4 covalent bonds by sharing electrons. Now silicon, which is just below carbon on the periodic table, can also form 4 covalent bonds, but you can't build a living organism out of silicon. The reason for this is the silicon is a much larger atom, so the bonds that can be formed are much longer and therefore much weaker, so it can't form the stable range of compounds that carbon can. Because organic chemistry forms such a large variety of compounds, we need some way of organizing them. So the first level is to divide them up into homologous series. So these are compounds with the same functional group. So they all have the same general formula. They have similar chemical properties. The key thing is that they've got the same functional group. So, for example, the one we're going to study, alkanes. There's also alkenes and alcohols. And those are just 3 homologous series. You could also have things like carboxylic acids, esters, nitriles. They all have the same functional group. So this functional group is important. It's the atom or group of atoms that are responsible for the chemical behaviour of the molecule. So, for example, if we go back to our 3 functional groups we looked at, we've got the alkane. Well, that's carbon single bondedly to other carbons, and we've got the maximum number of hydrogens present. It's what we call a saturated molecule. So there's an example of an alkane. That would be ethane. We could have alkenes, which have a carbon double bond. They are called unsaturated because they contain at least 1 carbon-carbon double bond, and they don't have their maximum number of carbon-hydrogen bonds. We can have an alcohol, which has an OH functional group with nothing else on that carbon. That is not a hydrocarbon because it contains an atom of oxygen, but it is an organic chemical because it's based on a carbon chain. So there are different types of organic molecules. The main type we have is straight-chained molecules and branched molecules. So a straight-chained molecule here, for example, hexane, there are no branches coming off the main carbon chain. Here, 2-methylpentane, we have a branch coming off the main chain. So this is the main chain of carbons here, and you have this branch sticking off of the main chain. We can have cyclic groups, which are made up of closed rings of carbon. For example, here I have 6 carbons, but they are in a ring. So this is called cyclohexane. Cyclo, if you see that, that just indicates I've got a cyclic group. In other words, I've got a ring. I could have a ring of 3, 4, 5, 6, and so on carbons. We can also have aromatic carbons. Now you won't be studying these until the upper 6th, and you'll be studying one compound in particular, and that is benzene, but you might come across it a few times in the lower 6th. It's more usually seen like this. We generally only draw this structure of benzene like that. We don't generally show the hydrogen bonds on a benzene ring. But again, it's a ring of carbons, but this time it's got this ring of delocalized electrons. Saturated compounds only contain these single covalent bonds, and they have the maximum number of hydrogen atoms possible. So again, hexane would be an example of a saturated compound. Whereas an alkene, for example, would be an example of an unsaturated compound. They contain at least one double bond, and you could add more hydrogen atoms, so they don't have the maximum number of hydrogen atoms possible, because you can add hydrogen across this double bond. So we can depict molecules using different types of formulae. So we're going to use pentane as our example. So the first thing we could do is we could give the empirical formula. You've come across that when we were studying moles 1, and it's just the simplest whole number ratio. So it's C5H12 in this case. I can't divide this by any numbers, so this is the simplest whole number ratio. Next, I've got the molecular formula, which just gives me the number of each kind of atom that's present. In our case here, we have the same molecular formula as we do empirical formula. The next formula we have is what we call the structural formula. And this is a little bit like reading the formula left to right across the page. So we have a CH3, CH2, 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 CH3 molecule joined together. Sometimes you'll see them drawn with the covalent bonds between the carbons, but more usually, if you're asked for the structural formula, it's this formula we're interested in. The displayed formula takes that one step further and gives us more detail about our molecule. It shows us all the covalent bonds, either single, double or triple, and all the hydrogen atoms must be shown. The problem with this formula is it does take a long time to draw out, and quite often we're not interested in these carbon-hydrogen bonds because they are very strong, very short and very difficult to break. Quite often there's no interesting chemistry going on around these CH bonds. Which leads on to the last type of formula, and this is called skeletal formula. In this case, you admit carbon and hydrogen atoms, and you also admit any carbon-hydrogen bonds. So it's much quicker to draw, and it concentrates just on the functional groups we're interested in. So we have this zigzag line here representing our pentane. So I've got 1, 2, 3, 4, 5 carbon atoms. Wherever you've got a carbon atom, you're going to get the hydrogens bonded onto it. We just don't see them because they're not all that interesting. The last one, and it's kind of outside of the box because it's not one that you're expected to be familiar with, but you may see it in some textbooks, and that is a space filling image. So that just gives you an idea about what the molecule would look like. So that just gives you a quick introduction to organic chemistry. In the next video, we're going to be going on and looking at naming organic molecules. So until then, take care, stay safe. Bye-bye.